for joining us today. We have another very exciting talk today, and from one of the colleagues at NC State, Dr. James LeBeau earned his undergraduate degree in material science and engineering from RPI. And upstate, then he moved to California to enjoy the weather, I guess. At Santa Barbara, he completed his PhD degrees, and after that he joined NC State in the material science and engineering department in 2011. He had a lot of distinguished awards, including Microbeam Analysis Society Distinguished Scholar Award, Ralph Junior Faculty Award, and R.M. Young Investigator Award. And the research group focuses on applying and developing transmission electroscopy techniques to determine the atomic structure of material defects. And today he'll be talking about the atomic structure and chemistry of bismuth, telluride, and calcinite interfaces, which is very exciting thermal material, and the clinical defect about that. So we are looking forward to it.
Thank you very much for the introduction, and thank you all for being here today, and thank you for the invitation to come and give this talk today. So already listed, we're talking about the atomic structure and chemistry of bismuth telluride on gallium arsenide substrates, and that we've used our latest CR instrument here at North Carolina State. So, of course, I have to start off by acknowledging my collaborators, my postdoc, Ryan White, my students, for all the work on this project, and collaborators at RTI International here in North Carolina in the Research Triangle. And work was funded by DARPA through contracts. So, for my talk today is as follows. I'll start off with a very brief introduction of thermoelectric materials. You're probably familiar with this, but I just want to go over it to give us a better background and footing on going forward. What they are and how they integrate with devices, particularly, and how they're relevant to the assist center. Then I'll go into discussing scanning transmission electron microscopy, comparing it with the more conventional microscopy, which you all might be a little bit more familiar with. Thus, the capabilities of STEM and its role in understanding material science problems. I'll go into electron microscopy, particularly on imaging resolution, and discussing our new state-of-the-art Titan microscope here at NC State. It has to do actually go in showing how it allows us to do atomic scale chemical imaging of our materials, really for the first time. And then we'll get to this bismuth telluride gallium arsenide interface and understand how those two materials join together at the atomic scale. So devices, what we have here is for having thermoelectrics is that some 60% of energy produced goes as heat. It's lost, right? So you can recover some of that heat, say, by one of these materials. You can increase the overall efficiency of an producing process, or we have applications where you want to scavenge heat from an environment, say the human body. You can do that. So those materials work is a heat gradient into electrical power. And to do this, you need a thermal and electrical conductivity mismatch. So your photons affect than the electrons through the material in a sense. All right. What this means is that the carriers ultimately diffuse from the material to another and up on one side, the cold side, produce a potential gradient. So you create an electrical potential from a gradient. All right. Now, so imagine that if you produce these couples between an N-type and P-type material, you can actually begin to extract from that, and particularly applications such as vehicle exhaust, where if you want to make your vehicle more efficient, power your air conditioner, for example, off of your exhaust, are some of the prospects for the future of these materials. Or in the case of the Cassini probe, if you're familiar with that, that's actually powered by the currently orbiting Saturn. That's actually powered by a thermoelectric. Okay, so bismuth telluride. Where does bismuth telluride come in? Well, it's a thermoelectric material, particularly for applications around room temperature, not particularly, but it's relevant for scavenging heat from either the exhaust of a vehicle or from the body. Right. Now, the bismuth telluride structure is rather complex. That's a single unit cell that I'm showing there. That hexagon, that big there is a single unit cell. And it's comprised of quintuple layers. So there are these 5 atom atomic plane stacks that then feed material. I don't know if my cursor shows up on the screen or not, but they're terminated by the T1 layers. Okay. So what I'm showing here also are 2 projections of that crystal structure down different crystallographic orientations. Now, the way we've done that is later in the talk, you'll see these projections again. All right, so when we start to see the structures, this is what you're seeing, is projections of the atomic structure down either one of these directions. Okay, that in the back of your mind, and you can sort of see where the red atoms terminate in double layers. The layers are actually held together by van der Waals forces. All right, the secondary bonding, not direct. There's covalent bonding or chemical or covalent between bismuth and tellurium, but valence between it ultimately does is increase thermal conductivity while maintaining electrical conductivity, making bismuth telluride a good thermoelectric. And it's also to be a topological insulator, if you're interested. So, how do thermoelectrics fit into a SIST? These sorts of that have already been shown at these talks, but really the whole idea, or part of the concept of the assist, from what I got from the website, is that it's all about wearable electronics and being able to monitor for long term the health of an individual, right? And understanding the exposure to different toxins and these sorts of health data. And long-term sensing. Now, if you have a long-term sensor either embedded in somebody, it has to have a way of powering itself, right? So that full factor can include a patch on somebody's body, a wristwatch, a tap on somebody's tooth. Those are on the website, and really to fit a variety of needs, right? A person now, if you look at it, a person gives off about 100 watts of heat. Your light bulb walking around, okay? And if we have that energy, these masses could be self-sustaining. They're power themselves off of your body, okay? And just an example here at the top, it would be more of a little region of red and green there. That'd be a thermoelectric device that then powers the chips and the sensors, okay? The example of this has been made previously. It was more of a proof of concept by Seiko, the watch manufacturer. And this a thermic watch down here at the bottom is a little thermoelectric generator that the watch, so you don't have to wind it. So there's been a proof of concept of these general efficacy of putting a thermoelectric on the human body. Okay. So the assist ecosystem, thermoelectrics really fit into being able to harvest energy and powering these devices. Okay, that's where we fit into this whole setup. Thermoelectrics fit in. Okay, just to give you a bit of relevance to today. Okay, so that was a very brief background of thermoelectrics and how it fits in. Okay. So what we need to do now is I go through a little bit of the background about scanning transmission electron microscopy, because it's still a relatively new technique, particularly when we're talking about a resolution and being able to explore materials. Okay. What you're more familiar with is the conventional high resolution TEM. Okay. So high resolution TEM, what we do is to take a parallel beam of electrons up there and down. They strike our sample. when they hit a sample, they diffract. Those that brought into interference with one another with an objective lens to form our image. That's a problem because these images are not direct structure images. They have an interference pattern in T. So as a result, doing something like simply changing the focus changes your phase shift between shapes. And I don't know if it's going to show very well, but that's uneventful, huh? Okay, so what it's meaning is bright areas in the image, in atomic structure images. Let me go to the next one, actually. So if this were an HRT image, it's a STEM image, but if this were an HRT image, the bright image would become dark, and areas would become bright. And the interpretation of those images, absolutely requires image simulations to understand where the atoms are actually sitting in these lattices. Okay, a bit of a problem. It slows us down. More importantly, these are not number-sensitive images. So because something's bright in HRT and doesn't mean it's heavier. Okay. But a lot of analysis that you have to do after the fact to understand your images. Okay. So STEM, we get around this issue. Rather than using a parallel beam of electrons, we use a very finely focused electron probe that crosses the specimen. But rather than SEM, we look at the electrons that go all the way through the sample, or something like 20 nanometers thick in this case. Very, very small electron probes, smaller than about angstrom in size or less at modern instruments. Scan that across and collect electrons scattered out to high angles, okay, with a annular shaped detector, that high angle annular dark field detector as it's called. Now, because collecting out at high angles with that annulus, we get two impacts. It's incoherent imaging, so the bright blobs are really where the atoms are at. You're seeing positions of atoms in these images in STEM, HRT, EM. Also, is that at high angles, it means scattering is Rutherford-like. So the higher the atomic number, the more we get at those locations. All right. Simply by looking at how bright the blobs are, we see how or what sort of atoms are in those columns. So I can directly say that those are strontium columns and titanium-oxygen columns, image intensity. There's another component in that, though, in that the number of atoms also matters, because we're seeing a projection of a three-dimensional structure, something maybe like 20, 30, or to 100 some odd atoms in projection at those positions. So it's not flat atoms. Okay. All right. So what's nice about this is that we can get simultaneous chemical information either through electron energy loss spectroscopy or energy dispersive X-ray. This is chemistry and electronic structure information. I'm going to go into about EDS because to our talk today. So material science, where does it play a critical role? Well, most characterization techniques, whether it's neutron diffraction, X-ray, SIMS, they really provide an average view of your sample. They have information from a large area. But I'll tell the whole story because what controls properties often is the single defects or defects localized to specific regions that you want to learn something about. And that's where STEM really fills in this gap at the bottom, because it allows us to explore materials at the atomic scale with direction. I can see where atoms are at. I can compare with models, compare with DT, understand our system much more thoroughly than we can just simply with HRT. Okay. As an example, I mean, here we're seeing a direct twin boundary up at the top there for gold. At the bottom, we see the direct interface between bismuth titanate, strontium titanate. And you can edge the location there. And basically a textbook example, you see the strain field around this location. All right. For engineering, what we really are techniques that can analyze our materials. And for structures, we want composition and size, we want dimensional information, and or for interface, or for instance, we want reconstructions. That means occupancies, displacements, or preparation of certain elements to an interface. Okay, and we also need, specifically for electronic devices, we really want to know what's the absolute dopant concentration. How many atoms of a particular dopant do we have in a device, say a p-type region? How many types of atoms, or how many atoms of a particular type? And that really makes a big difference as we go smaller and smaller devices. I mean, we're pushing 20 nanometer barrier now, I believe, in fabrication and production. So as more and smaller, it's just going to matter more and more. So I've already shown you that we can determine the atom positions, and at least to some degree determine type if we know the chemistry beforehand, right? We have with strontium titanate. We also count the number of atoms, and this is something that I was involved with quite a bit developing. Is, can image intensities be quantified directly from theory, and does that mean we can actually count the number of atoms in the sample from our STEM images by using theory? So I'll just talk about this. So our STEM image is really divided into two parts at atomic column. All right. So when we sit at an atom column location, are set up very quickly at that position, and the atoms that are in that column significantly impact the observed. As the probe continues to propagate through the material, it begins to see other atoms surrounding it, and as a result, the content of the signal actually is more just background. It doesn't contain any localized information. It's all spread out. We can get information about a certain depth. Say first four in this case. This is all exaggerated, but in portion we start to get signal other columns within our images. Okay, we directly quantify these, particularly for this portion. We need to calculate theoretical images and compare with experiment. We can predict what the image intensity should be. So compare between an experiment. We need measuring experiments on an absolute intensity scale. Simulations, what's been done is that simulations report STEM image intensities on a percentage of the incident probe. Okay. Now, what ultimately means is we just needed to do the same thing for the experiment. We need saturating detector response and witnesses. So what I've done is to do all of those steps. We've been able to ambiguously compare theory and experiment with STEM. So going through all this is to really show that STEM is a very powerful tool for material science and some of the state-of-the-art aspects of the field. Okay, so just for a comparison here, we have our experimental images on the top of strontium titanate at 55 and 105 nanometers. Bottom, we have theory, that's simulations, and there's a perfect agreement between the two. So what to come out of this is that quantum mechanics works. We can really predict what ions do as they pass through the sample. It's just a big quantum mechanics experiment in a box. Okay, and effectively interpret these images. Now, what that has allowed us to do with STEM is actually begin to count the total number of atoms present in our material. So by going the way around, using to tell us the atoms we had in our sample. All right. So in this case, we just have a sample of gold. Each one of those numbers there represents the total number of atoms in that atomic column. So what we've done is effectively turned the STEM into an atom counting machine in a standardless atom scale. All from quantum mechanics, we can predict how many, or we can tell how many atoms were in our image. Okay, and it weighs about, or there's 10,674 atoms in that area. Or, I think of gold. Okay. Now, now that we've gotten through what the past STEM is, we can get to our new scope here at NC State, okay, and how it's really changing on microscopy and material science and what we're able to achieve now. So, what to tell you is that the electron microscope is built of electromagnetic lenses. Those lenses, under like eyeglass lenses, are absolutely horrible. They're defective, effectively. The inherent limitation, the ability of those lenses to focus electrons, and they call spherical aberration. So in the world, all rays emanating at a point would, on the other side of that, focus to a single point. With traditional electron microscopy lens, rather than coming from reproducing a point, electron outer edge of that lens get deflected strongly, so they end up getting focused at a different point. Okay, so truly what we've had to do is to and after our into a beam path to limit the ones that we're contributing. This reduced our resolution dramatically. Okay, and So the aperture size based on the wavelength of our electrons. So as you increase energy, the wavelength goes down, and the spherical aberration coefficient is fixed. Okay, for a microscope. But as you increase your aperture size or decrease your as limit aperture size, so you make it smaller and smaller, your resolution goes down dramatically. So at the top there, that's a small aperture, which is something like what we'd have to have for TEM. Our resolution goes to crap effectively. Okay, and as you increase that aperture, then ideally you'd come back to more of a point detection, to detect closer and closer spaced atoms. So resolution for previous generation microscopes was completely limited by the wavelength and the spherical aberration, and you stuck with the microscope you bought. Really, if you wanted higher resolution, you had to buy a new microscope. Of resolution is stagnated in the 90s. So I mean, dramatic improvement in resolution up until about 90, and for a long time it more or less stayed flat until about the middle of the 2000s. The final approach to get around resolution was just go higher energy, right? So you had energy and wavelength, just keep pumping up the energy. So buying these huge countries were buying these huge microscopes. In Japan, 2 stories tall. It goes up 1 million electron volt microscope, and to get to something like an angstrom resolution for a comparable instrument at 100, you go from 2 to 1, a factor of 2 improvement. But $10 to do that. Okay, so that's not really an ideal situation. You had maybe 5 in the entire world. All right. The approach is to use, is to use an aberration corrector. That aberration corrector combines different elements to produce negative spherical aberration. Aberration, when passing through our objective lens, ends up zero aberration. Negative plus positive would be 0 if you can match them. So what that means is that you can 0 CS as you increase resolution dramatically, or you can open up that aperture size then and resolution to beyond sub-angstrom. You can add energy as well, so it becomes independent of energy primarily. Okay, so you can image sub-angstrom at 80 kV, for example, rather than 300. And then tens of millions, we just have a few million rather than tens. And the aspect of this is that it also allows us to open up our aperture size. Okay, so open up our aperture, we can pack electrons into a smaller area. What that means ultimately is we can get more analytical signal from the generation of X-rays from sample, and actually begin to map out chemistry at much smaller scales. Okay, complicated devices. There's some 16 elements here. But what enabled us to do is go from an example in figure there, that's down the 110 zone axis. And what, I mean, you can sort of see some features, but with a microscope, you can go and produce the image on the right, which is an improvement, right? Tons of contrast, and all separated atom columns. So each one of those cells represents 2 columns of silicon. The addition here is one of these microscopes, an FEI Titan, and it comes aberration corrector with this ChemiStem EDS technology. I'll talk about this just more in a moment here. So, this is when you have a state-of-the-art instrument like this, you have to have a state-of-the-art room. So after spending quite a good sum of money, hundreds of thousands of dollars to renovate the room for this microscope, we achieved really the stability needed for imaging with this scope, all right? So we have radiant cooling panels to keep the temperature room very fixed at with less than 0.1 degrees Celsius change per hour to environments that need that sort of temperature stability. And airflow. Basically, we don't want our microscope operator to asphyxiate, so we have some air in the room. Background fields and vibration isolation are essential. We build room inside of a room to keep the microscope isolated from the rest of the building. Okay. So, with respect to, I've mentioned this a couple of times as I've been going through X-ray spectroscopy. Well, how are X-rays generated as electrons pass through? Well, as they pass through the sample, we end up collecting some of those electrons with our core electrons in the elements. All right, the core electrons, the back down to ground state, gives us an X-ray emitted. All right, those X emitted are characteristic of the elements present. Now we collect it with something similar to down here. This typical setup is this silicon lithium detector. Terrible collection efficiency. Only 3 steradians. That's important because if the detector would be a complete sphere, you'd collect all electron rays emitted from the sample, all X-rays. Perfect sphere is 4 pi steradian. So we're only 1% of the X-rays actually generated in our sample. That's pretty awful. And the large size of the detector down there at the bottom, you can see, it's pretty big. I mean, that's about 1.5 foot, that Dewar sitting there, tall. Just to give you an idea of scale, that's pretty, that'd be put multiple detectors inside the microscope to improve efficiency. And that's where this Super X detector goes, this STEM technology that I said. What is, other than 1 detector, we have 4. These are all detectors. They're basically p junctions that hit, and that we're able to actually collect our X-rays significantly faster as well. So you get very fast output. And labels is a collection efficiency. It's almost an order of magnitude greater with the microscope. So rather than 0.13, we can get up to 0.7. Very important, because what we can do is actually begin to map small very quickly. So gold palladium particle down up here at the top, and you see the core shell structure. That's acquired in just 5 minutes. Normally, it takes over an hour to achieve that that number of counts in that image. So, dramatic improvements. More importantly, what we do is, rather than this simple black and white image at the bottom here of strontium titanate, we only know what it is because we knew beforehand. Yeah, well, we can now map the chemistry to atomic resolution. Those are not just black and white columns. Those are green, and being able to correlate chemistry at each single position. So for titanium and which ones are strontium, straight without any real analysis for that. Atomic chemistry is now possible and across the entire periodic table. And really tantalizing correlations. This is some initial data here from gallium arsenide, which is pretty relevant to hearing. But here, indium and gallium, and again, it's down to 110. So those 2 columns spaced next to each other there in the top. All right. And see from the map is that gallium and indium go to the same positions, as they should. It's a substitutional alloy of those 2 elements. And arsenic. So you can actually see the polarity of the crystal structure, where all the arsenic are, where all the indium gallium. But more importantly, where those go are the indium, where indium appears bright, gallium is dark, and where gallium is bright, indium is dark. A correlation between the chemistry and which means there's the prospect in the future for actually quantifying at the atomic scale how many elements are, or how many atoms are at each position. And this is a pretty big deal. There's a lot of complication going further, and that's where we're heading towards. Okay, so fine, we can get into physics right now, that your background of and what it is and why it's important. Okay, nanoscale dimensions of thin film enable integration with devices and property engineering. So as you make things thinner, you begin to be able to control properties, such as being able to make super lattices of bismuth telluride with, say, antimony telluride. You can improve the thermoelectric behavior dramatically. An example of that in a moment. But with common semiconductor substrates is really essential for integration, right? So whether it's gallium arsenide or silicon, we need something to put this on. The problem is the very large lattice mismatch between those substrates and bismuth telluride. There's even a symmetry mismatch, because for the arsenide 100 surface, you go a square surface of gallium arsenide to a hexagonal growth plane for bismuth telluride. That you would not think would like to grow nicely on top of one another. Just a refresher here, I'll flip through this, but again, when you're looking at these images, the projections are the difference in rotation around the crystal structure, that when you different structures of these two types, right? They're just 30 degrees rotated relative to one another between those two. Okay. Integration requires substrates. Growth on 111 silicon has been reported. There's hexagon on hexagon epitaxy in that case. So we wouldn't expect it to be a terrible we wouldn't expect it to be a particularly difficult process, okay? Now, the problem is that with ADF stem imaging, you see sort of a reaction layer there at the interface. That's not an abrupt interface. You see how the smear, that's not generally. That means that some of bismuth or tellurium have probably moved into the silicon, which potential to cause problems when you're talking about doping of the silicon substrate. You're using the local chemistry across that interface, all right? And edges like this introduce defects. You can sort of see one right there if you look closely. That modifies the structure, okay? And they sort of see the same thing. I mean, you get a mismatch going up the direction there between the layers. Okay. So, is that samples have also been grown epitaxially on 01 gallium arsenide. This is this hexagonal epitaxy. It should not really be possible to this level of epitaxy. The nearly perfect epitaxy. You can't see it here because he's HRT. I'll show you in a minute. But lattices of devices of aid, and their ZT, this thermoelectric figure of merit, how good it is greater than 4. Normally, in most material, or not greater than 4, greater than 2.4, and normally that's around 1. So by controlling the nanoscale dimensions, we can impact how materials behave. Okay. Now, I'd like you to note is look. You can tell much about the of that thin film from these ATEM images, or the top one. You obviously see a defect there at that. No, right? I will in a bit on what these things actually look like. But just that in mind about as we go forward. HRTM has not provided a very clear understanding of these interfaces. So in collaboration with RBI International, and we've gone ahead and taken a look at some of these interfaces. This is the 001 interface between gallium arsenide and 001 bismuth telluride is that hexagon on square. Okay. Now, from HRT imaging were not a direct image of the structure. They were an inference pattern. They did not have the chemistry at that interface. Aberration-corrected STEM, a high-angle angular dark field STEM, which is show an atomically abrupt interface. Remember the silicon case where it was kind of smeared out? With this, we have an atomically abrupt interface, a single, just growing the bismuth telluride straight on top of that substrate. Okay. So possible. How are we getting such epitaxy? Because this is common throughout the entire interface, localized region, the TM representative area. This is typical. We perfect epitaxy of these films. So how is this possible? We expect in film epitaxy. Here's the gallium arsenide substrate surface. Okay. Putting the telluride on top of that. I mean, some alignment every now and again in terms of the periodic nature of this, but that's about 3 nanometers periodicity. There's a match. So again, we not expect this. This concept of van der Waals epitaxy comes in. So when having direct chemical bonding between your thin film and your substrate, if you put all of your dangling bonds on the substrate, what you're actually just put another layer of something like bismuth telluride on top of that without chemical bonding, but secondary bonding effects, van der Waals, forces, our whole film to the substrate. That's provides a way around close lattice matching, because at that point it doesn't really care the atoms are at across that interface, and you have consistent symmetry. You can go from 6-fold to 4-fold in the case of cube to hexagon, and it provides epitaxy highly mismatched structures. So here's just some examples. I mean, where you have a dangling bond that's not going to be stable. All right, but a gap produces a nice interface. So look through the top of this film through the substrate. What we find is that we have that model, just that simple hexagon on cube. So this is an experimental HADF STEM image. Bright lines are corresponding to high density of atoms. So probably this lines here. We're seeing that missing or that fringing exactly you would expect just from a very, very specific model. All right, those are laying right on top of one another. Cube. Okay. Look at that interface. I already showed this, but let's take a closer look at what's going on here. So there's an epitaxy relationship. In this, it's 1 of gallium arsenide to the 1,2O of the hexagonal telluride. All right, or in this case, given the way that's mapped out. But here, in the bismuth telluride, at the interface, something interesting is going on here. Very atom columns. Those are more than the gallium arsenide. And in fact, you take a line profile across that image, that's just extracting the image intensities at box. Well, it is bismuth telluride. So that's a bismuth column. That's a bismuth column. That's, I don't know. And you can see it's quite dimmer. Okay. Now, patients here. One, and the common one that would be made is that bismuth is going to that interface. Bismuth is somehow interacting and lining up at those positions. The alternative interpretation of that is that there are actually more atoms, because the type of atoms, it's the number of atoms at that location. So you get more of something else at the positions. For them alone, we are left with an ambiguous answer. Okay, but that super X comes in, because we can explore materials and entry of materials simultaneously at atomic resolution. Okay, so separate for slides. I'm going to skip that slide. It just says EDS is the only way to do this, really. But resolution image maps, and we see straight away we have our arsenic, gallium, tellurium, bismuth. The only one sitting there is thorium, not bismuth. Line profile across the chemistry now. We can separate out where all the bismuth and tellurium, and look what's sitting at the interface. It's only bismuth. All right, it's only tellurium. It's only at that interface. And more atomically resolved. So the interface, you see the tellurium peak at the middle there. Right? The tellurium is peaking to position in the middle. Okay. But tellurium sitting there, and in fact, you can see in the gallium arsenide where the arsenics are on the left of that dumbbell at that interface. Gallium is bonding. So gallium is directly bonding to tellurium. Okay. Seeing that map, we get this beautiful example of, you can see all those purple locations there are the atomic resolved, perfect face, or beautiful interface that we've been able to explore previously. So, well, what means is that at the interface between these two materials, there's a second phase forming, or a third phase forming, a quarter unit cell of gallium telluride structure. Telluride would have the zinc blende crystal structure, same as the substrate, so it makes some sense as to what's going on there. What ultimately means is that the telluride is acting to cap off the substrate. It's removing arsenic, capping the substrate, and capping angling bonds ends up providing for telluride growth. Okay. As I mentioned before, let me actually go a step. So as I mentioned before, we have these HRT images that look really quite bad, and we can really directly interpret what was going on there. Well, we can go and look at these directly. So it's an obvious step. You see all the atoms, you see everything going on. We also see the chemistry of the layers. Okay. If you follow the these layers are bismuth, and the next brightest in between are tellurium. So these, we know that. Okay. So being able to follow a line across the interface, see how an easy way to point to this for everyone, but you just have to follow across there. But as from going from left to right, you actually see that bright row sort of darker. So across that interface is a tellurium layer becomes a bismuth layer as meet up. Okay, so the secondary step size, you see steps much smaller. There's a less effective region in this. It's a this defect in the bismuth telluride film at that position. Ultimately, what this means is that by controlling the step size of the substrate, we have the potential to engineer the properties of the materials. Right? By putting larger steps, you can cause more distortion, or in smaller steps, you can cause less distortion, or by forcing the size. What it means is that you can scatter phonons. What these steps ultimately mean are that you're scattering phonons across that boundary, so you're able to engineer the thermality of the films these regions. So it puts in decreased thermal conductivity, right? And there's that. Okay. And when we all observed quite frequently about these films are that other types of defects are also present. So in case, what it ends up looking like the tire tread, right? It looks something left behind by your car, but across the van der Waals gaps of the bismuth telluride structure, you're basically reflecting mirror translation, or a mirror plane at this in here that leaves behind defect. again, defects are going to modify the phonon density of states and cause either thermal conductivity or electrical conductivity. And again, by modifying and controlling this, there's being able to modify and engineer these materials at scale to give the properties they desire for thermoelectric devices, whether it's or heat scavenging for energy efficiency. I'd really like to conclude with, I mean, the new microscopy techniques are truly disruptive in terms of what they're able to do for science, right? They've 10, 15 years ago, this would have been unthinkable, and now it's become routine. With techniques, or with these techniques, we can go back to problems that have been studied 20 years ago and find entirely new things that were overlooked because they're just beyond our resolution limits. We couldn't look at them. And what we do this is, I mean, this telluride grown on these films have been around for 10, 15, 20 years now. And to actually understand that interface has only been made possible through these technologies. And for telluride, we saw why it grows epitaxy on gallium arsenide in the first place. It's that we're running a third phase through that boundary that allows us to separate the two. By able to directly study defects, we can begin to understand how to improve materials. Even we can understand how to improve materials further at the atomic scale. So with that, I'd like to leave you with a little bit of microscopy art. Thank you for your attention.
Thank you, Jim, for an excellent talk. Questions from the audience here?
It can grow pretty much as thick as you want. I mean, the films have been growing microns thick. And between the substrate and the film, strains are all released. So in that case, it really doesn't matter per se about how much thicker you go. Your defects, you have more twin boundaries as you go, just from the ways through the growth, but it will grow pretty epitaxially. I mean, it's going to be a nice structure. Question. So the question for those, So for those external, the question was, if we had other surface termination, would we still get epitaxial growth? The only reported growth that I've seen, I believe, is arsenic terminated. I'm not sure it's just that that it's the arsenic termination that matters the most, or if it'll grow something else, some other term. Let's see here. Oops. So the question was, what's the thickness of the TE sample? And I mean, in this area, we're probably looking at 10 to 10 nanometers thick. It was about how the sample is prepared, and it was prepared by conventional polishing and milling. So the question was about resolution EELS and whether or not this could be used. The answer to that is no, because you cannot easily resolve bismuth with EELS. bismuth matter. They're not the best elements to go mapping. So ES is really the only way this could have been done. Well, for STEM, it really doesn't matter. So, I mean, it just matters in that how densely you're collecting. Normally, these images are required by 1024 by 1024 pixels. That's your minimum size. So you go to 2048 by 2048, it will you'd still get atomic res at a much lower magnification. So it doesn't really matter. I mean, resolution isn't really directly related with size, other than yeah, 4 pixels. Okay, for the absolute atom counting example, the simulations versus experiment, those simulations were calculating the absolute intensity. So the percentage of the beam intensity that was coming onto the detector, the electrons, effectively.
Okay. Let's go. Are there questions from anybody online?
Are there questions from anybody that's on WebEx? Second. No?
Are there other questions from the audience here? Stephen?
So whether or not the hexagon on QTAXY was seen in other systems, I believe it has. I mean, especially if you're able to have this van der Waals gap, particularly normally if there was direct bonding, it should not occur nicely. I mean, there are cases where the lattice parameters are close, get epitaxy, but when there's dramatic mismatch, it becomes very difficult to get nice epitaxy, especially if it's coherent over domains. So the question was about why the experimental images in the comparisons between theory and experiment were a bit more wavy than the experiment. It is due to thermal drift. That one was not on this Titan here. This was on a different microscope. So this, with microscope here at NCSU now, that should not happen to that level of distortion. There's some distortion, but it's not nearly as bad as on that instrument. And was about whether or not an energy minimization could be done to figure out how these crystal structures are really aligning relative to one another, the gallium arsenide and the bismuthite. And I mean, absolutely. I mean, one of the next steps in this is to really understand the impact of that on the phonon density of states. And I think that particularly connection with EPITAXY would be really essential to push further to understand the impact of it in the line down one particular direction relative to another.
Jim, you mentioned where you revealed the results. You mentioned that brightness of that interface there could be because of bismuth or more atoms or something there.
Yep.
At the end, why was the blue brighter?
Oh, okay. Right. So the question was, why was the thorium brighter at the interface? Well, because in the zinc blende structure, it would mean that there's twice the number of per unit length down the thickness. Yeah, through the so compared with telluride. With telluride, there's many fewer atoms of radium for the same thickness. So the question was looking at cadmium telluride interface with gallium arsenide. I mean, so correct me if I'm wrong. I mean, the zinc blend structure, right? Yeah. So that should go nice. That should be a nice epitaxial layer right on top of or low parameter mismatch. I mean, you're going to have defects, but in that case, I think you'd have more interfacial defects than probably what we're do to see anyway.
Okay, no further questions. Let's thank Dr. LeBeau one more time.
The assist note that there'll be an all-hands meeting of the assist faculty, students, and any staff and industry members. So we'll give you information about that. And I think our next seminar is in 2 weeks. So we'll see you next week. Thank you.